Welcome back, focused learners, to another explainer. Today, we're diving into what is honestly one of the most fascinating technological shifts of the last decade. We're going to break down exactly how Apple completely disrupted the entire computer industry. And get this, they didn't do it with some flashy new software trick. Nope, they solved massive hardware problems using custom silicon. So if you've ever wondered how modern laptops suddenly got so crazy fast, completely silent, and basically never die, let's figure it out together. Seriously, think back to before 2020. You'd open up a couple of heavy programs and suddenly your super expensive, professional-grade laptop starts sounding like a jet engine, literally preparing for takeoff. It was so loud, right? Not only that, but heat is just radiating through the keyboard, and you watch your battery indicator absolutely plummet. You're getting maybe 5 hours of life if you're really lucky. So why did 2019 professional laptops sound like jet engines and die so fast? Today, we are going to understand exactly why that was happening, and way more importantly, how they fixed it. Okay, let's dive into this. Here is our roadmap for this explainer. First, we'll look at the Intel throttling problem, then the M1 architecture revolution, climbing the performance ladder, refining power with the M2, the M3 nanometer leap, and finally, the system-on-a-chip's secret. We're going to make total sense of all that heavy technical jargon and tie it directly to the real-world impact on your daily workflow.
All right, kicking things off with Section 1, the Intel throttling problem. To truly appreciate Apple's massive solution here, we really have to understand the severe limitations of those pre-2020 Intel x86 chips.
So, before 2020, every Mac ran on Intel chips. Now, these processors were undeniably powerful for sure, but they required a massive amount of electricity. And all that power draw generated a ton of excessive heat. When those chips got too hot, they actually had to protect themselves by automatically slowing down. We call this thermal throttling. It's kind of like buying a Ferrari, but the car literally forces itself to only drive 60 miles per hour just because the engine is warm. That is exactly what was happening to professional MacBooks. You paid for premium performance, but the hardware physically crippled your workflow just to keep from melting.
Eventually, Apple decided they just had enough. Look at this stark contrast. During the Intel era, users were suffering through high-power draw, overheating, those jet engine fans we talked about, and a really depressing 5 to 8 hour battery life. But Apple knew their iPhone chips were already incredibly efficient. So they stopped waiting for Intel to innovate and just decided to build the Mac processors themselves. And wow, the resulting Apple Silicon era delivered highly efficient, completely silent machines with mind-blowing 18 to 20 hour batteries. This wasn't just some fun side experiment, it was an absolute necessity for the survival of their computers.
Which brings us to Section 2, the M1 architecture revolution. This is where everything changed.
In 2020, the computing industry experienced a massive architectural shift, moving from x86 over to ARM. And this M1 release wasn't just a one-off event. It was a shockwave that laid the foundation for rapid, compounding innovation over the next 3 years. It set a crazy new baseline in 2020, which allowed Apple to scale up to the Pro, Max, and Ultra tiers in 2021, refine everything with the M2 in 2022, and then make a huge microscopic leap with the M3 in 2023. But let's rewind and look at how that initial 2020 revolution actually worked.
The biggest immediate challenge Apple faced was, well, the language the chips spoke. Intel processors use x86 architecture, but the new Apple Silicon uses ARM architecture. Imagine having an entire library of software that suddenly can't read the new computer's language. Total disaster, right? To solve this immediate compatibility problem, Apple created Rosetta 2. It's basically a live software interpreter that instantly and perfectly translates old Intel x86 instructions into the new ARM instructions. And it does this completely seamlessly. Most users never even notice this highly complex translation happening entirely behind the scenes.
But the innovation wasn't just about translation, it was really about how the chip handled memory. See, traditional computers have completely separate memory banks for the main processor and the graphics card. Because of that, data constantly has to be copied back and forth between them. That wastes incredible amounts of time and battery life. So Apple introduced unified memory architecture. This is a single pool of ultra-fast memory shared by the CPU and the GPU. So the crucial point is, by eliminating that constant copying of data back and forth, they saved so much power. That is exactly what led to that insane jump to an 18 to 20 hour battery life.
16 billion. That is a massive number. The 5nm base M1 chip actually packs 16 billion transistors onto one single piece of silicon. And they organize these using what's called a big-little architecture.
Basically, out of 8 CPU cores, they used 4 high-performance cores for the heavy lifting like rendering or gaming, and 4 efficiency cores built just to handle basic stuff like web browsing and background apps. Those efficiency cores barely sip any battery at all. All right, moving on to Section 3, climbing the performance ladder. Because once the base M1 proved laptops didn't have to compromise, Apple had to scale this architecture up for different professional needs. So let's walk through how they did that. The base tier is fantastic for everyday users, but developers and music producers, they needed more. So Apple introduced the Pro tier, bumping up to 10 CPU cores and 16 GPU cores, allowing programmers to compile huge Xcode projects way faster. Then for cinema and 3D artists, you've got the Max tier, boasting up to a 32-core GPU and 64 gigabytes of RAM. I mean, that is perfect for editing heavy 8K video timelines. And finally, the Ultra tier, which literally just doubles those max specs for extreme high-end workstations. And that brings us to this absolutely staggering number, 2.5 terabytes per second. Back when people thought the M1 Max was the absolute limit, Apple dropped the M1 Ultra. But here's the wild part. Instead of designing an entirely new, massive chip from scratch, they used a custom interconnect called Ultra Fusion. This literally stitches 2 M1 Max chips together, transferring data between the two halves at 2.5 terabytes per second. That is so insanely fast that the Mac operating system simply sees both chips as one single gigantic processor. Which obviously leads us to a very practical question. Who actually needs the immense power of the Ultra chip? Seriously, a processor with a 20-core CPU, a 64-core GPU, and up to 128 gigabytes of unified memory? That is a massive amount of computing overhead. So what kind of professional workflow demands that level of raw power?
Well, these ideal workloads include things like massive 3D scenes, full-scale cinematic movie production, and huge scientific simulations. Honestly, for a casual user just browsing the web, this chip is massive overkill. There's no way you need it. But for those extreme professional use cases we just mentioned, the M1 Ultra became one of the fastest workstation chips ever released. Let's shift gears to Section 4, refining power with the M2.
Introduced in 2022, the M2 generation wasn't really about a total revolution. It was an era of critical refinement and very targeted hardware additions. Now, what's really interesting here is the media engine. Instead of forcing the main CPU cores to sweat, overheat, and drain your battery while you're exporting a heavy video, Apple built dedicated physical hardware right into the chip solely for encoding and decoding heavy formats like Progress, H.264, and HEVC. The media engine handles all that heavy lifting, making your video exports dramatically faster while consuming way less power. Just a brilliant refinement. And that sets up Section 5, the M3 nanometer leap. This is where things get really small, but really powerful.
3. This single digit represents the new 3-nanometer fabrication process. The M3 family was the biggest technological leap since the original M1 because of this massive change at the microscopic level. By shrinking the transistors even further down to just 3 nanometers, they could pack substantially more of them onto the silicon. The end result? You're getting even higher performance paired with even lower power consumption.
With the M3, Apple also completely overhauled the graphics architecture by introducing something called dynamic caching. Let's break that jargon down. See, traditional graphics cards kind of just guess how much memory they're going to need for a task, and then they lock that memory down. That means a whole lot of it goes completely unused and wasted. Dynamic caching, though, allocates GPU memory in real time exactly when it's needed. This drastically reduces wasted memory, which gives you far better GPU utilization, boosted frame rates, and of course, even better battery life.
The M3 also brought 2 incredibly cool visual technologies to the Mac for the very first time: hardware ray tracing and mesh shading. Ray tracing physically simulates how light behaves in the real world, giving you those incredibly accurate, realistic reflections and shadows. And mesh shading? That handles complex 3D rendering at much higher frame rates. Together, these specific upgrades make a chip like the M3 Max perfectly capable of rendering incredibly realistic lighting in AAA games, or running heavy machine learning models locally on your laptop without even breaking a sweat. Finally, we arrive at Section 6, the system on a chip secret. Let's summarize the underlying design philosophy here.
Performance per watt became the new standard. This right here is what makes the entire Apple Silicon lineup so utterly dominant across the industry. By packing the CPU, the GPU, the neural engine, the media engine, and the secure enclave all into one single piece of silicon, Apple virtually eliminated latency. They proved to the entire PC industry that raw clock speed isn't everything.
You don't need to push clock speeds and literally melt your laptop just to get good performance. Architectural efficiency is the real secret weapon.
So, I want to leave you with a provocative thought from our source text. If you had to explain this architectural revolution simply to a friend right now, could you do it? Or did you just memorize the sounds of the words? Truly try to internalize the mechanics of what we covered today. Go out there, share this knowledge, and try to do one hard thing today before your brain has time to negotiate you out of it. Thanks for learning with our explainer today, and we'll catch you on the next one.